guys to do 514 elective. You're supposed to do, I think, 5 courses, right? 5 major courses and 2 electives.
Yeah.
I would advise that you should take 514, FINA 514, as one of the electives. It's quantitative method, it's continuation of this course. It's Megaoja who is teaching it. It will help you, especially if you want to do PhD. Because if you have to do PhD, you cannot escape from econometrics. No chance. Econometrics is a major course. And if you are doing econometrics in PhD when you have not done 514, you face a lot of difficulties. So I advise you should do it. I have course mates we are doing PhD together. Some of them did not take this course at master's level, and now they are lost. With me, I took this course, and I took this course last semester because last semester was my last semester for masters. Then now I'm doing PhD, so it's making my life easy. So I'll advise for those who like econometrics. I think I should share my screen. Okay, I hope it is shared. Let's give you. Let's see. 1997 to what's the end date? 2021. For the variables, GDP, inflation, unemployment. Delete. Okay, let me generate lane. Let's use lane. Generate lane GDP equals generate lane inflation equals employment equals employment. Okay. I have my variables on eViews. I have 3 variables. So let's assume I want to run a simple regression. Let's assume I want to GDP equals constant plus beta inflation slow. This is simple regression, right? Because we have just one independent variable, inflation, and we have GDP dependent variable. So let's assume we want to do this simple regression. I want to show you something. Of course, come to quick estimate. So I'll just type GDP. Okay, lane GDP constant lane inflation. This is my regression output, right? Okay, you know how to interpret coefficient. You know how to check significance using t-statistic and probability value. For t-statistic, we use rule of thumb. It should be around 2 or greater than 2 in absolute value for it to be significant, right? And you know the null and the alternative hypothesis. Null hypothesis, I think I should write it because I want to show you something. Null hypothesis. What's the null hypothesis? This coefficient or constant, whatever we are trying to test, is equals to 0, right? So let's say coefficient, or let's say this beta equal 0. Alternative hypothesis is that B is different from 0. So you check By the way, if you look at these T statistics, they are all significant, right? They are greater than 2. So if it is greater than 2 in absolute value, we can reject the null hypothesis. So you can reject this hypothesis that it is not significant. Equal to 0 means not significant. And you accept the alternative that it is different from 0, which means it is statistically significant, right? If you use probability value, you will get the same answer. Probability value is less than 5%. Of course, we can use 1, 5, 10%, but let's focus on 5. So if it is less than 5%, we can reject the null. So you have to be careful. If you're using T statistic, your T statistic should be greater than the critical value. If we want to know the critical value, we are supposed to look at the T distribution, but because we don't have the T distribution, that's why we use the rule of thumb. So the rule of thumb tells us that the critical value is 2. So if it is greater than 2 or around 2, we reject the null. So for T statistic, it should be greater than critical value for you to reject. But with probability value, it should be less than significance level or your alpha for you to reject. That is fine. And again, before you interpret these coefficients, you must make sure it's significant. You don't interpret insignificant coefficients. I'm done with that. Okay, now I want to focus on quality of the model. With the quality of the model, we can talk about the R squared, we can talk about the adjusted R squared, and we can talk about the F statistic. Actually, we can talk about all these things, but these three things I mentioned are the main things. What's R squared? Like, it is the coefficient of determination. It shows you the explanatory power of the model. What do I mean by explanatory power? Look at this model. What are we trying to do with this model? We are trying to explain the variation in GDP. We are trying to explain how dependent variable varies. And we have independent variable, and then we have error term, right? Now, this model right up to this level is the explained part. Error term is the unexplained part. You understand? So error term is the part that our model cannot explain. That's why actually we have something like this. Total sum of squares is equals to explained sum of squares plus residual sum of squares. So this is the explained part and this is the unexplained part. We don't want the unexplained part to be big. If the unexplained part is big, it means the model is not good. So that's why we ordinary least squares minimizes U terms. It minimizes the residual sum of squares. And I can remember in your exam, the guy will just give you 2 models and ask which one is better. The one which has the lower value for residual sum of squares is the better model. Because in regression, ordinary least squares, what is ordinary least squares doing? Ordinary least squares is trying to draw the line of best fit by minimizing error terms. So it is minimizing the residual sum of squares. So we don't want U term to be high. Okay, I'm trying to go off topic. Like, why do we square anyway? Don't bother, it's not important. So that is it. We have this model. This is the explained part, and then U term is the unexplained part. You get it? Okay. So our R squared, what is it? Coefficient of determination is 97%, right? So it tells you that the explanatory power of this model is 97%. And this unexplained part is only 3%. So the model has a high explanatory power. You understand? So it means that this inflation is very useful in explaining GDP. That's why the explanatory power is high. You understand? So in other words, you can see 97% of the variation in GDP can be explained by the variation in inflation. That's how we explain R squared. Now, adjusted R squared. Actually, adjusted R squared is still R squared, right? But it is something, it is the adjusted one. Why is it necessary to have an adjusted R squared? It is because in regression, we want to have a high R squared, right? If you have a high R squared, it means your model is good. But it is not all the time that a high R squared means your model is good. You can still have a high R squared even if your model is not good. How possible? It is because whenever you add regressor to your model, your R squared goes up. Like you see this model, I have just one independent variable, right? If I add a second independent variable, even if it is a useless variable or a useful variable, the R squared must go up. It is a must. But now, how do I know if the increase in R squared is because the model is better or it is because I've added a variable? That's why we need adjusted R squared. So this adjusted R squared is like a punishment process. Whenever you add a new independent variable to your model, this adjusted R squared will punish the model a little bit. Like it's like a penalty. It penalizes you for adding an additional model to your, an additional variable to your model. So with this adjusted R squared, there are two things which are happening. First of all, when you add a regressor or an independent variable to your model, two things happens. One, your model becomes better, like the fit is better, like the model fits the data well. And then secondly, there is a punishment process, punishment for adding extra variable. So what happens is that this benefit of adding the variable, if it is higher than this punishment, right, then it means your adjusted R square will not go down too much. But if this punishment is higher than this benefit, then your adjusted R squared will go down. That's why we need to check the difference between adjusted R squared and R squared. We should check. You see, the two values are very close to each other. Anyway, this is simple regression. You cannot see the difference too much, but I'm just explaining. Check R squared and adjusted R squared. If the two values are close to each other, it means the variable which has been added or your independent variables are good in explaining what is happening to dependent variable. But if there is a big difference, let's say this is 97 and let's say this one is 92. There is a big difference between your R squared and your adjusted R squared. It means that that extra variable you have added is a bad variable. It does not, it's a useless variable. It does not explain what is happening to dependent variable that much. You understand? So that punishment process is important. And again, I'm insisting is because whenever you add a regressor that is independent variable to your model, whether this variable is useful or useless, your R squared must go up. It is a must. But it is the adjusted R squared that will tell us if that variable is a good variable or a bad variable. So that's why adjusted R squared also shows you explanatory power. But since it has this punishment mechanism, the difference between R squared and adjusted R squared tells us if our independent variables are actually useful or maybe some of them are useless. You get the idea? Okay. F-statistic. Now I will show you something. What I have done here is t-test, right? T-test. We are testing the significance of each variable independently, individually, t-test. But with F-statistic, we are testing the significance of all the independent variables together. It's a joint test. Let's assume it is a multiple regression. Let's say we have here, let's say here is B1. Let me show you something. Plus B2 let's say we have this multiple regression, right? So you see here we have one independent variable and second independent variable. You know, simple regression, you have just one independent variable. But with multiple regression, you have more than one. So with t-test, we are testing these coefficients individually. We are testing if this beta 1 is significant. And we will, after that, we'll test if this beta 2 is significant. So we'll test them one after the other. That's t-test. So t-test, we are testing the significance of the coefficients individually. But with f-test, And of course, with t-test, we use a t-statistic, right? With f-test, we use a f-statistic. With f-test, it is a joint test, joint significance. We are testing if all of the dependent variables, if the coefficients of all of them are significant at once. So how can we write the null hypothesis? Null hypothesis is beta 1 equals 0 and beta 2 equals 0. Or alternative hypothesis, beta 1 is different from 0, or beta 2 is different from 0. You have to be very careful. You see here I use the word and, but here I use the word or. You can remember Kwanoja used to always ask us this in his exam. Because when I took this course, Kwanoja was teaching the course. At times you might get confused. In writing this hypothesis, with the null hypothesis it is and with the alternative it is or. Why? And yes.
Because in the model, to reject the null hypothesis, both of the variables should be rejected. The other,
yes,
it doesn't matter.
Okay. So with the null hypothesis, we are saying that all of the variable, all of the coefficients are equals to 0. Each of them. This one is equals to 0, and that one is equals to 0. If there are 3 coefficients, you see this one equals 0, and that one equals 0, and that one equals 0. But for the alternative hypothesis, we need just one to be different from 0. We don't want all to be different. If all are different, fine. But if at least one of them is different from 0, then we say that it is significant. So you must not have all of them different from 0. If just one is different from 0, it's enough. But with the null hypothesis, all of them must be equal to 0. So you have to be careful. So this is how we write the hypothesis for f-test. The null hypothesis is saying that this coefficient is equal to 0 and this coefficient is equal to 0. Then for the alternative hypothesis, we are saying that this one is different from 0 or this one is different from 0, right? So these are the hypotheses for the f-test. Okay, now that we have seen the hypothesis, the next thing is to look at the probability value. Where is it? Where's my avios? So look at this probability value here, probability of f-statistic. It is 0, right? 0, right? This probability of f-statistic, 0.
Yeah.
It is 0, which means it is less than 5%. So since it is less than 5%, it means we can reject the null hypothesis, right?
Isn't the model is for one simple regression?
Yeah, this is for simple regression, but I'm just trying to explain to you how f-statistic is working. I'll do multiple regression briefly, if I have time. So I've showed you how to, okay, this model is for simple regression, but I'm assuming that this is a multiple regression because I want to demonstrate something. So we are looking at the probability value. It is 0, right? So it is less than 5%. Therefore, we should reject the null hypothesis. So we are rejecting this null. What is this null hypothesis telling us? This null hypothesis is telling us that the coefficients are jointly insignificant. For t-test, it is telling us that that particular coefficient alone is insignificant. But for f-test, it is telling you that all the coefficients together are insignificant. So if we reject it, it means we are accepting the alternative, which is telling you that at least one of them is significant. Therefore, what does it mean? It means, so how can you conclude here? What you can conclude here is that after you have said everything, probability value is 0, which is less than 5%. Therefore, we reject the null hypothesis at 5% level of significance and we accept the alternative hypothesis, which means that our coefficients are jointly significant. You must put the word jointly. And then you add one statement, which means that the model is the model fits the data well. You understand? So if your f-test tells you that your coefficients are jointly significant, it means your model is of best fit. It fits the data well. But if you cannot reject this null, which means that the coefficients are jointly insignificant, it means your model is not of best fit. So the model does not fit the data, right? So that's how we interpret F-statistic. Okay. These other things here, Akaike information criterion, Schwartz criterion, Hanna-Quinn criterion. On their own, they are not too useful, but we use them to compare models. Let's assume that we have this model, and let's say we have a second model, we do regression, I have a second model, and you are trying to compare the two models, which one is better? Of course, you can compare them with R squared, you can compare them with all other things, but we can also use this criteria, these three criteria to compare two models. The model which has the lower value, not the higher, the lower value for each of these criteria is the better model. And again, when I'm talking of lower value, I'm talking of absolute value, because at times you will see negative values. So always think of the absolute value. So if you're comparing two models using this criteria, look for the model which has the lower absolute value of these values. The lower value, it is the better model. So that's how you can interpret those kind of things. Debye-Watson statistic. Okay, you say you have done the assumptions, right? The 11 assumptions, actually 10 plus 1 assumptions. What happens is that you will do it detailedly now after the midterm. Before the midterm, they just mention all the 10 assumptions to you. But after the midterm, you will do I think 4 of them detailedly. You will do normality, you will do heteroscedasticity, you will do autocorrelation, and you will do multicollinearity. I think, yes, you will do like 3 or 4 of them detailedly. So when you will be doing autocorrelation, that's when Miguel will talk more about this Debye-Watson statistic, and I'll also tell you about it. But if you want me to tell you about it now, I can tell you. This Debye-Watson statistic, it indicates to us if our model has autocorrelation or not. And again here, look at this value. It should be around 2, closer to 2, because you see this value ranges from 0 to 4. This value will never be negative, and it will never go above 4. It is between 0 and 4. Now, if this value is 2 or around 2, it means there is no autocorrelation in the model, right? But if this value is different from 2, let's say it is between 2 and 3, or it is between 0 and 2, then it means there is autocorrelation. So if the value, if it is between 0 and 2, that is less than 2, it means we have negative autocorrelation. No, sorry, we have negative autocorrelation. But if it is between 2 and 4, that is above 2, it means there is positive autocorrelation. Anyway, you don't need to know those details. Just know that if it is around 2, there is no autocorrelation. But if it is far from 2, maybe closer to 0 or closer to 4, then it means there is autocorrelation. For now, just understand it that way. Okay. I think I should run now a multiple regression and then tell you what I want to tell you. So we have lean GDP, constant, lean inflation, lean unemployment. So you see, this is multiple regression because we have now more than one independent variable, right? When you run this regression, you get the same. Delete. What's happening? Yes. Okay. So you see now that this is multiple regression, right? You see that we have now 2 independent variables here. And of course, we have our constant, right? So it is the same way we are interpreting. It is the same everything. We can use t-statistic, probability value to check if these coefficients are significant individually. That is t-test. We can use F-statistic and its probability value to check if these coefficients are jointly significant, F-test. We can talk about R squared, we can talk about adjusted R squared, whatever. But while interpreting these coefficients, there is something slightly you have to mention, which I'll tell you. But before telling you that, let me tell you one thing. One thing you should know is that adjusted R squared can never be higher than R squared. Never. It can either be equal to the R squared or lower than the R squared. Why? Who can tell me why? I've explained already. There is this R squared, this adjusted R squared will never be higher than the R squared. Best case scenario, it will be equal to the R squared, but most of the time it is lower than the R squared. Yes.
Because R squared is explain how those variables or how the model is fitted to our regression. Just R squared it explains how those variables are fitted and like tests like punishment.
No, I get what you're trying to say. Actually, R squared shows you explanatory power. Adjusted R squared also shows you explanatory power. Adjusted R squared is R squared, right? But it is the adjusted R squared. So whatever R squared is telling you, adjusted R squared is telling you the same thing. But the only difference is that with this adjusted R squared, there is a punishment mechanism for adding more variables. R squared shows you the explanatory power of your model. How much variation in your dependent variable can the independent variables explain? That's R squared. Adjusted R squared still shows you explanatory power. But the difference is that, as I explained to you, whenever you add extra variables to your model, the R squared must go up. Of course, we know that a high R squared means the model has a good explanatory power. But if you add a useless variable which cannot explain anything, the R squared will still go up. So if you look at just the R squared, you might think that the model has a very high explanatory power, which is not actually the case. Because if you add useless variables to your model, it will not increase the explanatory power. The R squared will go up. So that's why we need adjusted R squared, because adjusted R squared will actually tell us if these extra variables are useful or useless. And why does it do it? Is because adjusted R squared does not only give us the benefit of adding variables, but it also punishes us for adding these variables, right? So if the benefit of adding these variables is higher than the punishment, then your adjusted R squared will not go down too much. It will still stay closer to the R squared. Most of the times, it can even be the same. But if the punishment is higher than this benefit, then your adjusted R squared will go down, and so there will be a gap between R squared and adjusted R squared. That's why you have to always check the difference between the R squared and the adjusted R squared. If the difference is too big, it means your independent variables are not all of them useful. Maybe some of them are useless. So that is it. I want to show you something. Let me write this equation. I'll take this off. So, by the way, this is lean. I should put lean here because it's log. Lean. It's always good to work with lean log, because when you take the log, it solves a lot of problems in your model. It solves heteroscedasticity, autocorrelation, non-linearity, so many things. Okay, looking at this model, the constant is 26, right? 26. So I'll come here and put 26. .93, or let's say 94. 0.94. Here I think it's 26.2. Yes, negative 0.06. It's negative 0.06. So we should remove error term. When you estimate the equation, you remove error term. Okay. How can we interpret this? It's the same, basically the same interpretation we did with simple regression. But in this case, we have to talk of partial regression coefficients. Very important. Very important in multiple regression. Actually, there are three things which are very important in multiple regression, but they are not important in simple regression. These three things, and I'll mention it later. Let me just talk about this partial regression coefficients. Now, what does this partial regression coefficient mean? This partial regression coefficient is telling us that in a multiple regression, that is, we have more than one independent variable, if we want to know the pure effect of one variable on the other, we must hold the other one constant. So if we want to know how this inflation affects GDP, we must hold unemployment constant. It's a must. Because if you don't hold unemployment constant, you will not get the pure effect of inflation, right? And if we want to know how this unemployment affects GDP, we must hold inflation constant. That's just the meaning of partial regression coefficients. So if that is the case, how do we interpret this? So how I'll interpret it is that 1%, okay, I want to interpret this inflation, how this inflation, why is it not highlighting? This inflation, I want to interpret how this inflation affects GDP. So what I'll write here is that 1% increase in inflation will cause 0.94%. Everything is percent because it's log, right? Percent increase in GDP on average. Right up to this point is fine, right? This is how we used to interpret, right? 1% increase in inflation will cause this percent increase, and it's increased because here is plus. This percent increase on GDP on average. I told you always mention on average. So this is how we interpret for simple regression, right? But for multiple regression, you must add this statement, provided the effect of unemployment is held constant. Very important. This statement is very important because if you don't hold the effect of the other independent variable constant, you cannot get the pure effect of that particular regressor you are interpreting. You get the point? And it's the same thing. If we want to interpret this unemployment, what we'll say is that why is this thing trying to do this nonsense? By the way, I'll leave 2:25 because I want to finish this thing. So I'll take extra 5 minutes of your time. 1% increase in unemployment will cause 0.06%. It should be decreased, right? Because of negative. Decrease in GDP on average. That's fine. If it is simple regression, we'll end there, right? But with multiple regression, we must hold the other one constant. So provided the effect of inflation is held constant. That's partial regression coefficient. It's telling you that if you want to get a pure effect of any regressor, you must hold all the other regressors constant. So assuming that we had more coefficients, let's say we had here financial development, let's say we had here trade openness, whatever. So if you want to interpret inflation, you say provided the effects of unemployment, financial development, and trade openness are held constant, you must hold all the others constant. If you want to interpret unemployment, you say provided the effects of inflation, financial development, trade openness. That is, if you're interpreting one, all the others must be held constant. So that's the only difference with simple regression in terms of interpreting coefficients. It's just this partial regression coefficients. And again, there was a question Kohan Hoja asked us in the midterm, if I can remember. He asked us that there are 3 things. There are 3 things which, actually 4, is it 4 or 3? That there are 3, let's say 3 or 4 things which are very relevant for multiple regression, but they are not relevant for simple regression. And these things are adjusted arrow squared, F-statistic, partial regression coefficient, adjusted arrow squared, multicollinearity. There are 4, multicollinearity. So you see, all these 4 things are relevant for multiple regression, but they are not relevant for simple regression. Why? With the partial regression coefficients, I've explained why. Because with multiple regression, you have more than one regressor. So if you want to interpret one, you must hold the others constant. But in simple regression, you have just one regressor. So there's nothing to hold constant, so it's not relevant, right? Now, with this adjusted arrow squared, it shows us the punishment whenever we add an extra variable to the model. So it means you have more than one regressor. But with simple regression, there is just one variable. So adjusted arrow squared is not important. F-statistic, we are doing joint tests. You know, T-statistic is just individual tests. But with F-statistics, we are testing if all the coefficients are jointly significant. So it's relevant for multiple regression. But for simple regression, since we have just one coefficient, F-statistic is not too important, because if your T-statistic is significant, then your F-statistic must be significant in simple regression. But with multiple regression, you can have cases where some of the coefficients individually are not significant, but if you do a joint test, maybe all of them are significant. You understand? And then multicollinearity, you have seen multicollinearity, right? Yeah. Multicollinearity is telling you that there is a linear relationship between your independent variables. If your independent variables have this linear relationship, strong linear relationship of, I think, higher than 85%, then you have multicollinearity. But with simple regression, we have just one coefficient. So it is not like it's going to have a relationship with another coefficient. So these four things are not relevant for simple regression, but they are very important for multiple regression. I remember he asked us this question in the midterm. Why do you want to go when it's not yet time? I see you fidgeting to go.
The time is up.
But I said I will leave at 2:25, so I still have 6 minutes.
I have no research.
6 more minutes and then you can go. Right? But I think I've showed you some interesting things. I know you have not done multiple regression with the Gahoja. And to be honest, she doesn't even know I'm doing this, because she never even wanted me to do anything with you. She wanted me to allow you to rest. But I don't want you to rest. That's why I said you must come. So I just promised her that I'm going to revise some previous things with you, which we have done. And now I'm showing you multiple regression. You will do multiple regression with her in class, and then she will tell me, go and do multiple regression with them. I'll come and then I will still do it again with you, but at least I've given you an idea. And one final thing I should mention before we go, I think I should stop recording because I don't want it to indicate in the records.